So for the module, Measures of Disease Frequency, this lecture segment will address risks and rates. So these are finally the actual measures. How do we measure disease frequency? These concepts of incidence and prevalence, but the measures are the risks and the rates that we use to measure incidence. So incidence can be measured using what I will call count data, which is I will call a risk, or person time data, which is called a rate. So very often you will hear people in biomedical sciences talk about the rate of this and the rate of that, and they mean the amount of it, okay? In epidemiology, we're going to be a little more specific and careful with our use of the word rate. Rate is going to be used when time is in the denominator. So if you are just counting things, you are counting them, and that's great, and there's good reasons to do that, but the parameter that we're estimating with the count, we're going to call a risk. When you're counting the number of things per person time with a time denominator, that is what we're going to call a rate. So returning to our graphic representation of incidence that we had earlier in this module, each horizontal line being a person in the population at risk, and the solid dot indicating the onset of the disease of interest. So we are measuring the incidence of disease in this population, and we've got all this nice data, and we've nicely measured incidence. So how are we going to turn that into some kind of quantitative measure? Okay, so the first thing we're going to talk about is something called cumulative incidence. So cumulative incidence is a simple measure of incidence based on count data. And equivalent terms for cumulative incidence are risk or incidence proportion. And in fact, you'll probably see risk very often. Cumulative incidence is kind of textbooky. You don't see it in published articles that much. Not sure how much you see incidence proportion. But to me, it's useful to use all three terms because incidence proportion and cumulative incidence are much more specific and descriptive of what we're measuring here. All right, so the cumulative incidence in a fixed population monitored over a given time period, the cumulative incidence is the number of incident cases divided by the number of persons at risk. So from our graphic before, the count of actual persons who experienced incidence disease during the observation period was C, and the denominator, the number of persons at risk at the beginning at time 0, was N. So C divided by N is going to be the cumulative incidence. This is a simple proportion, so the term incidence proportion works out fine. The caution about cumulative incidence, however, is that cumulative incidence can only be calculated from a closed population. That is to say, you must have complete follow-up on each person. So, an example of application of cumulative incidence. 45 people attend a picnic. Within a week after the picnic, 11 of them were diagnosed with salmonella. So the incidence proportion of salmonella was 0.24. 11 divided by 45. 60 patients underwent surgery. 9 of those patients had complications before discharge. The risk of in-hospital complications was 0.15, 9 divided by 60. Okay, cumulative incidence. Prevalence is usually expressed as a proportion or percentage also, the number of prevalent cases, the number of persons in the population. So based on these examples, epidemiology sounds really easy, and actually the arithmetic, yes, is pretty darn easy. However, how often do we actually study a closed population? We really need to think about incidence in a dynamic population and how to measure that. In many research settings, instead of a closed population, we will be faced with a dynamic study population. People enter and leave our study population at different times. So this leads us to incidence density, which is a measure of risk with a person time denominator, which is more useful in this situation. In fact, most populations are dynamic. New people can enter the population after the start of observation. People might move away, people might die, researchers might lose contact with some people. So we talked about incidence being measured in a defined population at risk, but getting that population at risk to all sit still while we measure them is hard. So now our defined population at risk may have different people coming and going from the population during the course of the study. So we need a measure for that. So we need the concept of person time for that kind of measurement. So each subject in our population contributes person time to the denominator equal to his or her time under observation and at risk. So again, time under observation and at risk are the keys here. So now here's a graphic, but instead of having all the horizontal lines go all the way to the right for people who were not diagnosed with the disease, now we're going to have people who are lost to observation. And we can also call these people censored. Statistically, they are called the censored observations. So people are observed for different periods of time, all starting at time 0. And if they're lost to observation, we're showing an open circle, they're censored. So we're going to calculate the incidence rate or the incidence density as the number of new cases divided by the person time at risk. So in this graphic, okay, I may have moved the numbers a little bit to line them up better since the earlier example. So each event that happens, you notice, is happening at a particular time during observation. So whether these are weeks or months or years, it matters. It matters the person conducting the study, but to our example, it doesn't matter. So say we're observing our population for 1 year from 0 to 1. So there are 4 people who are diagnosed with our disease, have new incident disease at time 1. And then there are 2 people from within the population that are not diagnosed, but that is the end of their observation. So they stop contributing person time. And then at time 2, a new incident event, another person lost to follow-up, and so on. So the idea that each person contributes person time according to how much time they are under observation for the study, what that means is that those first 4 people at the top contribute 1 unit of person time, because that's how long they went before they were diagnosed with the condition. But down at the bottom, so the line at the very bottom that goes all the way from 0 to 6, that person contributes 6 units of person time. The second from the bottom contributes only 1 unit of person time because that person was lost to observation. So the person time is how long they were observed, regardless of whether they were censored or whether they had the disease event at the end of their observation time. We just want to know their person time for the denominator. And then the numerator is going to be the number who actually had the disease event. So can we calculate an incidence rate for this graphic? We can. So in terms of the numerator, we're going to count how many blue dots there are, right? How many people had onset of the disease of interest. So 1, 2, 3, 4, 5, 6, 7, 8 will be our numerator. That's the easy part. And then the denominator, we need to add up all those little orange numbers, which count the amount of person time for each person. So I'm not going to try to do that in my head. If you want to pause the video and add those up, you're welcome to do that. Okay, so there's 24 rows total. So the correct answer is going to be 8 over, I believe it's 96, because that's the sum of this person time. So 8 over 24, you are not correct. The 24 rows are no longer relevant here. It's the number of units of person time, which I believe is 86. Okay, so for an incidence rate, the units are reciprocal time. I just love that phrase, by the way, reciprocal time. An expression of an incidence rate must include time in the denominator. So when people call something a rate, again, people just casually talking about some kinds of numbers in biomedical sciences, they love to say the rate of this, the rate of that, but often they just meant the amount, the count, the quantity, whatever. When we say rate in epidemiology, we're going to say it's going to be a number per unit time. So if we said that annoying censoring and person time is too much of a nuisance, let's just try to calculate an incidence proportion from that graphic that we showed before, where some people were censored before they got to the end. So suppose we just counted everyone who had a disease event and everyone who was free of disease at the end of observation. What if we took those people who were lost to observation, who started in our population at risk, were lost at time 1, were lost at time 2, were censored? What if we just ignored them? Then we would say there were 8 diseased from a population at risk of 18. But would the result of that calculation be biased? Yes, it would. And in fact, it would be biased high. You would be ignoring person time contributed by people who are valid members of the population at risk who did not get diagnosed at disease. So if you ignore those whole people, what happens is that you have counted the incident events among the people with a shorter observation time, but you've ignored the person time. So once you have a dynamic population, you cannot ignore this person time concept. The other alternative would be to imagine that everyone who was censored at a particular time probably never got the disease, and just have it be 8/24. That would also be a bias, because you don't actually know what happened during that unobserved time. So you'd be then biasing low because those people continue to be at risk of disease. So the person time calculation is necessary to avoid bias. Okay, it's not just to make it fancier. It's actually because if you have people with different amounts of time under observation, any other way of counting them as whole units of people is going to introduce bias in your measurement. So when we estimate incidence from data with censored observations, we are making an assumption. We have to assume that disease incidence among the censored subjects after they are lost to observation for the study is the same as among the overall population at risk. So we're assuming that the incidence rate, the incidence per person time among people who are lost to observation, would have been the same as the people that we continue to observe. And so often when you're making a statement about a population with a lot of censoring, you have to be prepared to explain what happened to something about those censored people to make the argument that that assumption holds. So, they were unable to be observed any further because they moved away. Okay, but did they move away because they were in bad health and we failed to know about their diagnosis of disease? Is there a bias in those people who were lost? So just the very simple concept of incidence, which sounded so easy when we had 45 people attending a picnic, in fact, measuring disease in itself gets complicated because of this idea of people lost to observation and of making assumptions about the incidence rate in the people lost to observation.